So in the last class, we have discussed this activation function, and then I also told you that why we need this activation function. So whenever you are going to design this fully connected neural network, just putting all the layers are not sufficient, because you know that if you just put all the layers, the combination of all those layers will be linear only, because every layer is linear only. Okay, so like it's linear function. So if you're just combining multiple linear function, that will again give you linear function. And we know that most of the problems what we have, those are like having non-linear nature. Okay, so for solving those problems, we need non-linearity inside the neural network, and that's why we use activation function. So activation function is like non-linear function, and this is being used along with the fully connected layer. Okay, so we already have discussed a lot this part. So let us go for the next part. Okay, so let's see the architecture, how to design the architecture, or how what are the things we'll be putting while designing the architecture, and then how to code it. Okay, so suppose if we have two layer neural network, so what we'll do, we'll be having the input layer. This is the input layer, and then we'll be having the hidden layer. Okay, and then we'll be having the output layer. So input layer is like your all the input values. So whenever I'm saying that you have to apply this thing on the image, so what we'll do, you will convert your image into vector. Okay, you know, like these all the things we already have discussed in the previous classes. So take image, convert into vector, and then you have to give to the neural network. So this first part, if you see here, this is just one vector, and here this is called input layer, and every value here is called input neuron. Okay, and then you will be having hidden layer. Whenever I'm saying hidden layer, that means I'm having W involved here. Okay, so that means you are going to multiply with W, and you know what is the purpose of W. W is like set of values, parameters. So your W will be multiplied with this input, and you will get this output values. Okay, so this is like one layer. Okay, this is called one layer that takes the input and it gives you the output values. And then you can see here like we have used two layers. So one is this, another one is this. So W1, W2. Okay, so W2 will take again this as an input, and then it will give you two values as an output. Okay. So this is like the designing, like how we are designing this, how many layers we want. You know that we need a lot of layers, a lot of W's in sequential order. Again, I did not say like I did not mention this activation function, but activation function will be there along with every layer. So maybe if you are applying this W1 here, then W1 will be multiplied with this input and then give you the output, and then after getting the output you'll be applying one activation function over that. So it could be anything like relu, whatever you are choosing, you just apply over that. Okay, and then you'll go for the next layer, and similarly the same thing, like similar thing you'll be doing for the next layer also. Okay, so this is called two layer neural network because we have one this layer and this layer. And why this is called two layer? Because we have two W's. So one W is taking the input, getting you the mid-level values, and then second W is taking this as an input and giving you the final values. Now we can go for the three layer also. So it's your choice how many layers you want to use, and it also depends on the problem statement that you are solving. So maybe for your problem statement, maybe two layers are not sufficient, then go for more number of layers. So this is three layers. So you have all the input, again vector, and then you take one W1 that will give you this feature, these features, take another W that will give you this feature, and take another W3 that will give you this feature. I'll come to like I'll come to the coding part. We'll go through one by one, designing, explaining size, everything. Okay, but this is just I'm giving you the overview how it is looking like. and how it will like how you will be designing the architecture. Okay. So in this way, you can design multiple layers. You can put multiple layers in between. Okay. And whatever layers are in between, those are called hidden layers. Okay. So one will be your output layer, and one will be your input layer, and remaining will be like hidden layers. Okay. So one W will take you from input layer to the hidden layer. Okay. So what, like first, if you're taking first W1, that will take the input layer, input values, and it will give you the hidden values. Okay. Then take the second W to W here. It will take this as an input and will give you this. And take the third W3, and that will take this as an input. It will give you the final value. Okay. So last layer is called output layer. Actually, these input and output, these are not layers. Okay. But vaguely we define it in this way, because you know that input layer is just input values. Okay. But in book they have defined in this way. So we are also going to follow that. So input layer is nothing but just taking the all the input values, just taking the image, converting into vector. Okay. That's all. And then we'll be having all the hidden layers to get the values. And finally, we'll be having one output layer that will give you the final values. Okay. So now just want to code it. How to code it? I think we already have discussed the dimensional thing, all the stuff in the previous class. I assume that we already have discussed. So let us see the code, how to make the code. Suppose you have given these three layers, then how to make the code for this. Okay. So you know that since we have input and we have one W here, W1, W2, W3. Okay. That means you need three W, W1, W2, W3. And then you also need one activation function, because we have to use that activation function after every layer. Okay. So let us define the activation function. So suppose we are going to take the activation function sigmoid. You know how to write the equation for the sigmoid. Fx equal to 1 plus 1 divided by 1 plus e to power minus x. This is the equation of the sigmoid. So now we are going to write this through the code. Okay. So what we do, we define this thing in again we are going to write code in Python and in NumPy. NumPy is one package in Python which is used for doing all type of scientific computation. So it is just it's very similar to the C, very similar to the array in C, but it is having a lot of extra advantages, or it is having a lot of extra features compared to array, which you might have seen in the case of C. Okay. So let us use that package and define all these layers as well as the activation function. So this is the first line where we are just defining the activation function. So what we are writing f equal to lambda x colon 1 divided by 1 plus np dot exponential. This is the function, already inbuilt function in the NumPy. So np dot exponential, and then we are putting minus of x. Okay, and then just closing the bracket. So this is the function. This is the function or expression that I want to do. But I have written this thing in a single line. Okay, and I have just written as a lambda function, because I should have written in this way, like definition, maybe function, like activation function, and then writing all the definition and then returning the statement. Okay. So I should go in this way, but I have written in this way only. Why? Because it is like when you are using lambda. Lambda is like you can write in a single line. Here, if I want to write, it will take a lot of maybe few lines. But if you know that your function can be written in a single line, then you can use the lambda function. Okay. So lambda, and it's very, very simple way of writing. So what we are doing here, we are just providing here. So here, if you just see, uh, this is the input argument, so that you will be giving to function, and then this particular thing will be calculated, and it will be returned, and that return value will be coming into f. So very simple syntax. Take x, do this computation, and return value, and finally that value will be stored in the f. Okay. So in a single line you can write function. So whenever you know that you can write in a single line, just go with the lambda. And now we have to define the input. Like we have to find the input. Without input you cannot do anything. So from where I should take input? So whenever you are going to solve the real problem, like any classification, object detection, any type of problem, you know that you will be having a lot of images, a lot of data that you can load, and then you can process it. Now, since this is it is like TOI example. So what we are doing, we are just taking the random input. So taking just random value from the normal distribution. It's just like TOI example. Okay. So what we are doing, since I know that I have 3 values in the input, so that means I want one 3-dimensional vector as an input. So that we are doing here. So np.random.randn, that means it's coming from the normal distribution. This is like for the normal distribution. So what we are taking, and this is the size of the vector. So 3, 1, 3 into 1. So we are making one vector of 3-dimensional. Okay. And then we are just putting values here. Three values. So, and those values are coming from the normal distribution. So it's like just randomly we are picking 3 values from the normal distribution. So it's like random values. Okay. And the next goal is to define the neural network. Okay. So let us assume that somebody has already given you this W1, W2, and W3. Because you know that we need 3W, W1 here, W2 here, W3 here. And let us assume that someone already has given you. So then the goal would be to take this W1 and multiply with X. Because for W1, your input is X. Okay. So you can see in the next line, W1, comma X, and NP dot function. So NP is like NumPy. Okay. So from NumPy, you are taking the dot, that is the multiplication function. So it's like, it's just like dot product between W1 and X. Okay. So it will do the multiplication of W1 with X, and whatever output you are getting from here, you'll add the bias. You know that every time bias is involved, and we already have seen this bias in our previous classes. So bias is just like making, it's like it's generally used for making the model more generalized. Okay, so if you don't put bias, that means you are restricting your W to go from origin. But every time if you are restricting your model to go from the origin, that's not the good thing, because maybe your model needs to shift maybe left or right, because that can give you more generalized model. So that's why what we do, we generally put the bias. There are also some other roles of the bias, which we already have discussed in the previous classes, but this is also we can say the main role of the bias. So we have added bias here, and then once we got the result from this, now you know that you have to apply the activation function. And you already have defined the activation function. So this is your activation function, F. Okay, so whatever result you got, you just apply. You can see here, this whole part will give you one vector, that is a 4-dimensional vector. So if I'm saying, if I'm going from 3-dimensional to 4-dimensional, you know what should be the dimension of the W1. That will be like 3 into 4, or maybe 4 into 3. So that this matrix will be multiplied with the X. X is having 3 into 1. So, and it will give you 4 into 1. Okay. Then so now you apply F over this. So F is your activation function. So activation function will be applied element wise. So for one value, so you have, suppose you got 4 values from this first layer, from this part. Okay. You know that you have 4 values here. So that means you will be getting 4 values. So now what you will do, you will apply your activation function on individual values. So sigmoid will be applied here, 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 and you'll get one new four-dimensional vector. Okay. And then that is the output of your first layer. Now this should be given to the second layer. And second layer will take this and it will process it, and again it will give you some output. So this is the second layer, that is your W2. Now W2 will be multiplied with H1 because you got the H1 from the first layer. And then again you will add the bias and then you apply the F activation function over this, and that will give you H2. So from second layer you are getting H2. Now this H2 is given to the third layer or third full W. So W3 into H2, and you are applying np dot function, and then you are adding bias. And this is the final output you are getting. So maybe if you have only 3 layers, then I'll be going in this way. Okay. So I've just given you the basic designing of the architecture, but let us see one full implementation of 2-layer neural network. And it's like written in only 20 lines. So if you are going to design neural network, only 20 lines can give you one, we should not say very good neural network, but at least toy neural network that can be used for doing some type of training. Okay. So let us start to understand this. So whenever you are going to design any neural network, first you have to use packages. So like you see here, I'm just importing a lot of packages. So these are like all type of functions that we need in this design. Okay. So what I said like at the starting, that NumPy is the we can say the best helper for you. So you import NumPy as NP. As means like you're just giving the second name for the NumPy. Okay, alias for the NumPy. So import NumPy as NP. So we are just giving the small name for NumPy. Okay, so first task is like you imported the NumPy, and then from the NumPy random, you're also importing the rand n. That is the normal distribution, because you are going to take the values from the normal distribution. Okay. Now the next part is to define the architecture and input. Okay. So let's go for the next part. Okay. So here what we'll do, we'll define the network and the input. So let us assume that we are going to process 64 images or 64 inputs at a time. Okay. Before going to that, let me just tell you what is the goal. So goal is to take the input and apply the matrix over that. So we are going to apply 2 layers. So what I'll do, I'll define the first. I have to define the input. What is the dimension of the input? So let us assume that we have the size of the input is 1000. So this part. Okay. So this is the size of the input. So you can see like B input. In Python, you can multiple values can be assigned to the multiple variable in a single line. It's very that flexibility is there. It was not there in the case of C, but in Python, 64 is assigned to the N, 1000 is assigned to the DIN, 100 is assigned to the H, and 10 is assigned to the D out. So in a single line, you can do it. So this is like we can say the beauty of this Python. Okay. Now, what I'm saying that I'll be having 1000 values for the input. So I'll start from the 1000 values. That means our input is having dimension 1000, and then I'll move to the 100 values. So you can see like H, like that is like your hidden dimension. So 1000 to 100, and then from 100, finally I'll be reaching to the 10. Okay. So I'm going in this way. That means like if I ask you like how many layers we want for this, so you can easily say the answer. So we will need two layers. One is W1, one is W2. Okay, W1 will take the 1000 values as an input and it will give the 100 values. W2 will take the 100 values as an input and it will give the 10 values. So two layers are sufficient for getting this. Okay. So this is fine. Now I have also added this 64. Now this 64 is, can you guess what is 64? 64 is number of samples that you are giving to the neural network at a time. Because you know that you are going to train your model in batch. So batch means you are giving a set of images at a time or a set of samples at a time. Because you have the GPU, you can process multiple samples in parallel because of GPU facility. Okay. So what we are doing, we are giving 64 in samples at a time. So 64 will be assigned to the N. Now things are clear. So we are going from 1000 to 100 and finally 10. 10, maybe 10 can be seen as a 10 classes or maybe 10 values that we want at the end. And this is the hidden feature because it's coming in between. So 1000 and then you are going to 100, then finally you are going to the 10. I have to define the input. Now we have fixed the size, but we haven't defined the input. So let us define the input. And also we need to define the output, ground truth, because you have to, like, whenever you are getting the output from this model, you have to compare it. You have to see like how good your model is doing, because this is the training part. So while training, you also need to see like how good your model is doing, because that should be maximized, or you can say like how bad your model is doing, and that like unhappiness or that bad score should be minimized. Okay. So for that you need the actual value also, actual ground truth also, or actual level also. Okay. So it means while training we have to define X, that is your input, and Y, that is your ground truth. So what we are doing here, now we are defining in this line we are defining the input. So you, like, we know that we have n number of samples. So your n is 64. So for every sample you have to define the input. So n is the first dimension, that number of samples, and second dimension is the size of the one input. So you know that in this case I need 1000 values because neural network I have to design in this way. So that means I need 1000 values as a input. So this is like n comma dn. So what it will give you, x will be of, will get the x of size 64 comma 1000. So you got this matrix. Okay. And from where we are taking all the values, we are taking all the values from the normal distribution. Okay. So now input is created. So it's like all the random values just for the TOI problem, but I put this thing for getting this whole thing, the understanding of like how to understand this whole thing. So that's why I'm just taking the simple example. But in reality, you'll be taking X, maybe X as a samples or images, Y as a labels or actual class. Okay. Okay, but let us understand this thing, because if you understand this thing, then it will be easy for you to develop any type of model. Okay, so you define the X here. Now we'll go for defining the Y. Okay. So this part is your Y. Now, Y, how many values I want for the Y label? So first you have to see like how many samples we have. So we have how many samples we have? We have 64 samples. So that means I need this n, because for every value, for every sample, I need the ground truth. I need the actual label. And then how many values I want for every sample? That you have to check with the final value that you are getting. So you can see like we are getting 10 values at the end. That means I want 10 dimensional vector as a ground truth. So if I say what would be the ground truth size, then that is this, y equal to n comma d out, and d out is like 10, So 64, comma 10. So this is your ground truth. So for every input, you have actual or ground truth values. Okay. So now we have generated the data. Okay, we have created the data set. So this is the first part, because first and foremost thing is like you need the data set. Now we have done that. We also have fixed the size of the like output from every layer. That means again this is also hyperparameter. So we also already have fixed the hyperparameter, but we have to also define the matrix parameter W1 and W2. Okay. So next part is to define the parameters or take the parameters. So how to define it? So let's see what should be the dimension of W1. Suppose you are going from 1000 to 100, then what should be the dimension of the W1? So you can say, sir, it's very easy, because it should be, I need W1 which should be dimension of what? 100 into 1000. So that it will multiply with this x. This is the x, I should say x, and x is having 1000 into one dimension, and these two things will be multiplied and it will give you 100 dimensional as a vector, and which I want to get here. So that means the size of the W1 will be of this 100 into 1000. Or maybe I can also write this in a vice versa way, like in vice versa, like maybe I can write maybe I can also say like this is 1000 into 100. It's fine now, because like if I going to multiply this thing with x, I just take the transpose of this and do it. So in any way you can do it. So here like they have defined in this way. That's in this way. So din, comma h, 1000, comma 100. Okay. So this is the first W that we are going to define. Now in this W, you have to fix, like we have to also put the values. What are the values that we are going to put here? So since this is very simple, this is just y problem, then what we are doing is just taking the values from the normal distribution. So rand n, like take all the values from the normal distribution and put here. So fill all the values here in this matrix from the values, put all the values in this from the normal distribution. Fill it. Okay. So we have filled it. We filled it. And now this is for the W1. Similarly, you have to do it for the W2. Now in the case of W2, your input is 100. This is the W2. Your input is 100 and the output is 10. So you have to again define it. So what is the dimension that we are putting here? Rand and h. H is what? H is 100 and d out is what? 10. So we are just making the 100, 10 dimensional matrix. That you know that W2 needs that this dimensional matrix. Okay. And then it will be multiplied with this input. Okay. Because for W2, your input is of 100 dimensional vector. So you have to multiply again. Since you know that 10 is coming first, then maybe either you should multiply, you should put this h before this and then multiply with this, or maybe you can put h here and take the transpose of this, so that the dimension of both will be matched. Because you know that for the multiplication, your number of columns should be matched with the number of rows here. So that you like it is like the like how you are doing the programming. So in that way, like you'll be just fixing the size of this. Okay. So now this is done. So now you have fixed the input. You have defined the input. You have defined the size. You already have defined the matrix W1 and W2. Now what the next? Now the next thing is go for the iteration, train it. Since we have defined it, now just go for the training the model, training the network. So what I'll do now for the training, you can like mainly what you do, you train the network in an iterative manner. Okay. So epoch by epoch. So let us assume that we are going to train this model for 2000 epochs. Okay. So, okay. Now in every epoch, you'll be getting the loss and you'll be doing the back propagation. You will be updating the weights. Okay. Again, we'll see all those things. Now in the first epoch, again, what we have to do we have to go forward. So you have this neural network. You take X and get the output. This is the first thing. This is called forward pass. You know that you have two sitting here, and first W1 will take X. It will give you output. That output will be given to W2, and W2 will give you the final output. Okay. So the thing should be defined, and that is called forward pass because your X is moving in a forward direction. So let's define the forward pass. So again, what I have said that for every layer, after every layer, in general, after every layer, we'll be applying the activation function or non-linear function. So first you have to define the non-linear function, like what non-linear function you are going to use, which non-linear function you are going to use. So maybe in this case, we are going to use sigmoid. So e to power x, this is the equation that we are going to use. So we have to also use this thing while defining this whole forward pass. Okay, so let's do it. How we'll be doing it? So what is the first task? If I give x to this whole network, what is the first task? The first task is like multiply x to this W1, and it has given the output. I should take Y1, and then on Y1, I applied the sigmoid. And that is giving you H. Okay. So this whole thing we got from the first layer. So this is your first layer. Okay. And you can see like you got H from the first layer. Now we have to go for the next layer. Now you know that for next layer. And again, if I ask you what is the dimension of this H, you can say it's 100. But it's not only 100. It's like 64, 100. Because you started from 64, 1000. So your NumPy is very, very smart. It can do the broadcasting. So like I have shown that this example for one image, but at a time, 64 images can be processed, or you can say like this W1 will be multiplied with every image from this. And for every image, you'll be getting 100 values. And since you have 64 images, you'll be getting 6400 dimensional vector. Okay. So this is happening in parallel, and that's the beauty of the GPU. Okay. So you got this thing. Now this is not the final thing. I have to go for the second layer. And the second layer is W2. Okay. So W2 will take the H and it will give you the final output because you have only two layers. Okay, so you can see here H into dot H dot H point dot W2. So it's getting your W2 is getting multiplied with the H, and that is giving you the final Y predicted. Now you know that this W2 is like using W2, you are going from 100 to 10 values. So here, if I say what would be the dimension here, you can easily say this will be 10, but not only 10, it will be 64, 10, because for every sample you are getting 10 values. So now you got the predicted. So this is your predicted output that you got from the model. But since you have considered starting W, so this is not the best W. So this is just the starting W. So that means it will give wrong. Okay, and that's why you want to train the model. But how should I proceed further? You know how to proceed. For that, you know like what is the next thing. So the next thing is loss. So just see how far your prediction is from the ground truth. Okay, and what is your ground truth? What is your actual? Your actual is this Y. So apply the loss between your ground truth and the prediction. Okay, so since this problem is like we are just considering this problem as a regression problem, that means this y is having all the continuous values, or just like values, and then we have to match these values with the value of the ground truth. But suppose you are solving the classification, then you could be having different thing, because in the case of classification, you will be using something cross entropy or maybe sigma this SVM based loss. But here we are considering this as a regression problem. So here you can use the maybe MSC, mean square error. Okay. So we have the prediction and we have the ground truth, and just find the difference between these two vectors. So we have to match this prediction with the ground truth. Okay. And that's why we are just finding the distance, and this distance should be minimized. Okay. So NP square is like a square function over this. Okay. So mean square error we are finding, and then at the end you are summing it. Why we are summing it? Because you have 64 images, you have 64 samples, and for every sample you have got 10 values, and for every sample you have the ground truth, and every sample is getting matched with the ground truth, and for every sample you are getting the loss between prediction and the ground truth. And since we have 64 such type of samples, okay, that those samples have been processed in parallel. So why not we find the average of this? Okay, so we'll find the average of this, but before that, why not find the sum of all the losses? Okay, so for finding sum of all the losses, you just apply the sum function here. So what it is doing, it's just finding the sum of all the values, whatever you have got after this. Sum of all the difference values. Okay. So this is just like one type of loss function that you are applying. And then we are just printing this. So print t comma loss, that means like just you are showing to the just showing on the terminal. So t is your epoch and loss is like how much loss you are getting in a first epoch. Okay, so just like one value will be getting. Now this is done. This is called forward pass. So in the forward pass, take x, multiply with every w just in a sequential order, get the prediction, and apply the loss function to prediction and the ground truth. That's all. And whatever you loss got, that is your final loss. So that is your getting. So maybe if I write the neural network, then it is just like I have applied two layers here, x, this, predicted, we have ground truth, find the difference between these two, apply the loss function between these two, and get the loss. That's all. Done. This part is done. Now, what is the goal next? The next goal is to minimize it. So for that, you have to find the what? First, you have to find the gradient. You know that you have to see how, like, what is the effect of this W over your loss. And that you are going to calculate using gradient. So gradient is the helper for you, and that we already have seen in the previous class. So next goal is to find the gradient of loss with respect to every variables or every, we can say, parameters. So that we'll be doing here. So this is the gradient finding part. So I'll not go into depth. I'll not explain this part because we have not covered this part till now. So I'll cover this part after completing this this whole stuff. Like maybe this session only, or maybe in the next session we'll be discussing this. So again, this is very we can say this is very crucial step, but we are not going to discuss now. We'll discuss this into the next class. Let us assume that we got this gradient. So what we have to find? We have to find the gradient of like loss with respect to W1, with respect to W2, And since we have also bias, so bias is also there. So I am not including here, but you also have to find this thing with respect to bias, because again you are also going to learn the bias. Okay, so let us ignore the biases, and let us assume that we have these two, W and W1, W1 and W2. So you got the gradient of W1 and W2. So you got the gradient of loss with respect to W1 and W2. So this is with respect to W1, this is with respect to W2. Now you know how to change the W. So for that you have the very basic formula. Let us take the SGD, as stochastic gradient descent. So that W1 equal to W1 minus alpha into like grade W1. This already we already have discussed a lot this particular concept. Then again, similar way we can do for the W2 also. So W2 minus alpha into grade W2. Okay. Alpha you have to fix it. So in this case, let us assume that we are taking alpha as a 10 to power minus 4. It's a very small number. You can see here. Okay. And then you do it. So the same thing we are doing here. You can see it's like W1 equal to W1 minus this, or I can say like W1 new equal to W1 old minus alpha into this grade W1. And the same thing is happening in this line. This is just writing in a different style, but the same thing what I have written here. And this alpha is like e to power 10 to power minus 4. Similarly, I am writing this W2 here. So W2 equal to W2 minus alpha into grade. So same thing is written here. So now you have updated the W. So this is called gradient descent. We already have seen. So now you can see like we have multiple steps. First one is like defining all the packages, then define the network and the inputs, then define the number of epochs, like for how many iteration you are going to do this experiment, and then you have to define the forward pass, like how the input will be flow. So just multiplying all those parameters with x. And then we'll go for the calculating the gradient, because we know that we have to apply the gradient descent type of approach for changing the W. And for that you need gradient. So this part is all about calculating the gradient. And then finally you have to apply the gradient descent algorithm. So either SGD or maybe Adam, whatever you want to do, you can apply here. So this is like one general process for defining the neural network. Now let's see some of the things, and then you guys can ask a question. So what has been observed that if we are increasing the neurons means the size of the hidden layers. So like suppose I told that I'm going from 100 to 1000 to 100. That means it is like 100. You have 100 neurons in this layer, or you can say 1000 neurons in the input layer. So if you are increasing this value, then there is effect on the neural network architecture. So what they have observed that by increasing, you are getting more capacity. That means you are getting more generalized, or we can say better network, better model. Better model means like it can give better performance. Okay. So here you can see like this type of structure, and by the and here a lot of mixing, a lot of values are like mixing. So you can say like this is your one class, this is another class, but you can see like there's overlapping. Some of the values from this class are going here. Some of the samples from this class are going here. So this is like wrong. You are getting wrong result in some cases. Then again, this is like when you are considering 3 hidden neurons. Then if you are going for 6 hidden neurons, then you can see like there is some improvement. Now misclassification is less. Even if you go for more number of hidden neurons, you can see like now here almost all the red samples are going in the red class, and other samples are going in a in this these are like two classes. So this is one class, red color, and this is like maybe orange color. So here this all the samples which belongs to the orange color, it's going into that cluster only, and all the samples which belongs to this red color, it's going in the that cluster only. So like while increasing the neurons, your model can give you more accuracy. But this is not always true. But in this scenario, they have observed that this improvement is happening when we are increasing the number of neurons. But again, it is there. It is only up to certain level. But if you're going beyond that level, then again anything can happen. But up to certain level, this is true, because if you just increase, your performance will be improved. We also have seen the effect of the regularization. So when I was discussing in the previous classes, like what is the effect of the regularization? You know what is a regularizer? A regularizer is just for making the model more generalized. Okay. So like you can use, we have seen that when we are taking lambda equal to this is like weight we are giving to the regularizer. So when you are increasing the weights, your model will be more generalized. But again, there is trade-off, because if you are increasing if you increase this value very high, then there is problem, because then and if you decrease your the main loss very low, then maybe your model will be underfitted. Okay. Or if you are not giving more weight here, maybe your model will be overfitted. So again, this is like here we have to take care of all the values, and again, so that's why this is called hyperparameter, because we are going to set it. Okay. So these are all the things we have seen. So one thing is like your first part is like when you are increasing the number of neurons, it will give you more capacity. That means more performance. And another is like your regularization term. So that's also affect, or it's also helping you to make the model more generalized. Okay. So you can also say like this can be also considered as a regularizer, because if you're increasing the number of neurons, then again model is getting you're getting more generalized model, or you can say the more accurate model. But what I'm saying this is not always true. It can give you up to certain level, but after that maybe it may fail. Okay. So what I'm trying to tell you, that this can be considered as a one regularization, like just size, the fixing the size. But this is not strong regularization term, because since what I said that after certain level it may fail also. So what we can do, don't give more focus on the size part. Whatever size you are taking is fine, but again it depends on the problem statement. So if your model is very, very complex, you can go with multiple layers. But fixing the size, like taking 100 or 10, you can also ask anytime. You can ask like why you have considered 100 only, why you have considered 1000. Input is like fixed, because every time you know that what is the dimension of the input. But in between like 100, or maybe you could be having, maybe suppose you are having 10 layers, then you can define the size of every layer, like what size output we are getting, we want to get from the particular layer. So that is in your hand, and that's why that is hyperparameter. And what I said, that when you increase the number of neurons, like suppose you are going from 1000 to 100, and then from 100 to 10, but suppose I go from 1000 to maybe 200, it may give you better result. That I have shown that if you are increasing the number of neurons, then what they observe, that it gives you the more accurate model. But this is not always true. It is only true up to certain level. So that's why you don't take this as a strong regularization term. You know what is regularization? Right? The goal of the regularization term is to train the model in a more generalized manner. And this is also doing the same type of stuff, because when I said that we are going from 100 to 200, then we are getting better model. So why not I should consider this number as a regression term, but this is not always true. So that's why in practice, you take only that type of regression term which we have seen in the past as a regression function, but don't take this number of neurons as a regression term. You can set this thing randomly. You can take like again by doing experiment, you will get to realize that how to proceed, like how many values I should take in the particular layer, how many, because you again whenever you are learning from the experience, you are learning from the past. So you can see like how people have done in the past, how they have done this thing in the past. Okay, how they have, because they have got good performance. That's why their paper got published or their work got published. So why not we should take idea from their paper? So we generally, when we go with this type of architecture, we take the idea from the previous, we just see previous papers and then take idea from that. Okay, and then we also design in that way. So though, so my what I was saying that do not take this size as a regression term. Instead, whatever regression term you have seen in the past, you just take that as a regression term, or maybe you can take some other regression term. Okay. Okay. So with that, maybe I'll stop. I'll pause here for 5 minutes. You guys could ask question. Yes. Any
So,
question, please? Huh.
yes, sir. Regulation and learning rate, both are same or different?
No, regression is like just we have seen like in the previous classes that suppose we are making this values small in the W. That is your regression because you are going to make the model more general or more simple. Okay. So that is like the goal of the regression is to make the model simple and more generalized. That is the goal of the regression part. But learning rate is like how you are moving, how you are taking the step while
Mm-hmm.
choosing the W. Okay, so suppose you started with one W, but you have to find the W which can give you the best result. Best result means your best accuracy, or you can say the loss close to zero. But the goal of the regression is not to make the loss close to zero. Instead, their goal is to make the model more generalized so that it will work good for the new unseen data set also.
Okay.
Did you get the point or I explain
Sir,
again?
means what I understood that in each and every iteration, we will have
Yeah.
some learning rate, right? So
Yeah,
that
learning
can
rate
be
is
variable.
fixed.
That will be fixed. And after some iterations, it means the weight will be standardized and it will give you the result means output, expected output to the
Hmm.
original output to zero, means in that way.
Close to zero, not zero,
Uh,
but close to. Our
so,
expectation is to get close to zero, but it maybe not very close to zero. So that depends on the problem, how complex your problem is.
okay, okay.
Huh. So
So
alpha,
now, mm,
this is the term. This is the term when you are going to train the model. This first term is your data loss. Maybe if you recall the previous classes, then
yeah,
I said that this is the data loss. Like it's giving the focus on the prediction and the ground truth and making your prediction close to the ground truth. So that
right.
part is happening. That is happening in this part. And second part, like when I said this, like this was here, what it is doing, it is just making the value of the W is small or low, so
Mm,
that you know that when I was discussing it, and then I said that if you are having larger value, then your model
yes,
will overfit
yes,
because your W will be having, it's like your W is more powerful than your X. So every time like
right.
whatever W is saying, that you have to like somehow you have to believe it or you have to rely
Yes,
it. Okay, so W is like it will be like more powerful. So that's why we don't want W to be more powerful. Instead, we want to also give some weightage to the X because X is also the guy because you are going to take the decision based on the X. So that's why,
yes.
since we know that in the X we have all the low values, so why not we also consider low values in the W, so that
Mm,
both will be having the similar type of influence.
yeah. So,
Okay, and learning rate is separate. Learning is just this loss, how we are decreasing this loss. So there your learning rate will help. So learning rate, like when we are optimizing, you are changing the W,
Hmm.
that in that W, like how we are changing the W, where it will help you. So that W equal to old, W new equal to W old minus
Yes.
alpha. Okay. So this is just like optimizing the loss, or you can say optimizing the W or minimizing the loss. So that is the aim of this alpha. Alpha is like how fast we are moving. I've just given the example like how we are moving from the mount, like suppose some hill to the ground. So how what should be the step? So your step is like your alpha. Alpha
Yes.
is just
Yes.
controlling the speed, controlling the speed.
Yes. 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 Okay.
Or any other question?
Sir, like, how can we use stronger regularization? Like, is it by ourselves or will the like algorithm will choose it?
No. So how it depends on the problem. So how complex your problem is. So maybe if your problem is not that much complex, whenever I'm saying complex, that means uh, it depends on the samples. Suppose you're solving two class classification problem, and maybe you have like a lot of overlapping images. That means if you're going to train your model, maybe your model will confuse. Suppose if you're taking the dog and cat, and a lot of cat images are very similar to the dog, or maybe a lot of dog images are very similar to the cat. So in that case, if you want to train your model for differentiating between cat and dog, it will be very, very difficult for the model. Okay. So that is, you can say like it is a complex problem. So if you have complex problem and you are solving, like you're finding the loss and then you are going back. Now, if it is not very complex, then maybe you can go with, or what you have to do, you have to try this regularization one by one. So maybe you can go with this, first start with the weight, just apply the regulation on the weight. So just reduce the weight, values of the weight. That is again, we already have seen in the past that how to like apply one L2, L1 on the weight, and then overall loss stuff. And then you have to decrease the loss, you have to decrease the main loss, that is your predicted between predicted and ground truth. This is the original loss, this is the actual loss. And then you also apply the maybe L1 or L2 over the W. That means I want a very good W. Very good W means like it will give the prediction very close to the ground truth, but at the same time I also want W which is having the low value, because I know that if W is having low value, then it will be more generalized, or it will be not getting overfitted case. Or in that, in other way, I can say like it will work well for the new samples. Okay, so this is one regularization. You can also try even advanced regularization term like dropout. Sometimes we just drop some of the neurons. Okay, again, we'll if we get time, then I'll also cover this dropout. We have a lot of different type of regularization term that we can apply. Okay, and then see
Yeah,
like
so
which one
is
is
that mean
working.
like, so
Uh,
like I'm asking like, is that mean we have to do it manually or is it done by the algorithm itself? That
no,
was
you have to do manually only. But nowadays we are making everything very like automatic. So again, we have one area, neural architecture search. So maybe you can use, or you can also make this automatic. So just give all the options to the model, and then you just let model itself decide like which one I should choose. So that can be also done. But
okay.
again, that
So
will take.
as
Uh,
okay, so it's like as we do force attack on something, it is similar to
yeah,
that.
yeah,
Like, we
yes,
provide pre-input
yes,
and it will check
yeah,
on
yeah,
that.
yes. You're right.
Okay, okay, got it.
Sir, in the area of defining the network, that's the first section of the entire code, where we
Yeah.
define input and we define the number of input layer, 1,000, and hidden layers
Mm,
also 1,000, 100, and then output layer is 10. So how do we
mm.
decide on those numbers in the code area?
That.
Yeah, that one.
Yeah,
Yeah.
yeah. That's why I said like this. These are like hyperparameters. So going from 1,000 to 110, it's just we are choosing these values randomly. Okay, it's not we're not using any logic here. But let me just tell you, when you'll be going to design some architecture, so you just see like what people have done in the past. So that's why I'll also explain all different type of architecture, like how what logic they have followed and how they have designed different type of architecture. Because this is like just designing part, how
Mhm.
we design it. Okay, so it's like you can also say me why you have considered this 100. Instead, you can take 200. 300, why only 100? So there is no any logic for this. Okay, so that's why what I've said, that people have shown that when we are increasing the neurons, like suppose instead of 100 if you are taking 200, that will give you better result, but that is also not true always. So don't give more focus on the that size of the neurons. Instead give focus on some other part. One is like your loss. If your model is doing good, suppose you have taken 1,110, and then your loss, you took the loss function, and then you do the back propagation. And what if you're observing that your model is doing good, like your loss is getting reduced very fastly, then you're okay with that.
Mhm.
Just take it. Okay. And then you can think about the regulation term. Okay.
Mhm.
Then you
Okay.
can take some other type like W1 regulation on the W1, or maybe drop out. You could take some other type of regulation term, but don't do a lot of experiment with this
Number of.
number of neurons, because
Okay.
that will again take a lot of time, and again it is not guarantee. It's not giving any guarantee that every time
I
you'll be getting the
understood that.
better.
I
Hmm.
understood that, sir. I missed the part of understanding the significance of the input 64 there. I would like to, I request you to one more time just explain that, sir. X, see, if I consider X as an input, if I consider image as an input, image is having a 32 by 32 size pixel.
Hmm.
So that will
Hmm.
give me a 3072. If I consider each pixel is having a 3-bit value, then that will give me
Hmm.
a 3772 size of an X.
Hmm.
That's an input
Hmm.
for me. Okay, and like that, I have got so many enough reference because I have got multiple GPUs to process. Each and every GPU will process multiple inputs like that.
Hmm. Hmm.
So if I consider X 3072 here as an input to
Hmm.
my model, where
Hmm.
does it reflect in the code here, sir? How can I correlate that input in your code here? 64, should I consider 64 as an input? Correlate, should I correlate to that?
No, your input dimension is this 1,000. So in your case, you are saying that if I apply image, so you
Okay.
know that first you have to convert into vector. So you'll be having 3072 dimensional vector.
Yes,
So
sir.
instead of 1,000, you have to provide 3072 here. Okay,
Okay.
and you are processing 64 such type of samples at a
Ah,
time.
so that's a batch. 64 is a batch
Batch,
size.
batch.
Batch size, and image size is 3072. And
Hmm.
I'm trying to converge those 3072 pixel size into 100 pixel size. Is that what
Yeah,
you?
3072 to 100, and then finally 100 to 10. So like you have, that's why you have two W, one W1 and then W2. So W1 will take the 3072 values and it will convert into 100, because 100 is like hidden features. So in between features you are getting that. Okay.
Mhm.
So from 100 3072 we are moving to the 100, and then W2 will take the 100 and it will give you 10. And that's why we have designed this two W1 and W2 in that way. So W1 will take the 1,000 here in this case, or maybe 3072 in this case, and it will give you H, that is your 100. Now W2 is this second one. Actually, this first part is for the W1, and the second part is the for the W2. Now second part, this W2 is like take the 100 values and give you the 10 values. It's like
Okay,
two
sir.
step,
Yeah,
two no,
we are here applying the random function to pick a value
yeah,
between.
it's just like 2i problem. But in reality, like whenever you are going to solve some problem like this CIFAR 10 problem, 10 classification problem, then again you have to define the actual size, and also these hyperparameter, these values could be choose. You can play around these values, but again your input will be with respect to the size of the your image. So in your case, like it will be like 3072 because you have to stretch the image. You just open the image and make the vector.
Yeah, make
Sir,
the
point.
I have a question. Like, if we are having a large data, like 30, 40 GB of data, then, sir, how much RAM is required to process that? Because if we are using deep learning, which is having 512 three hidden layers and having nodes 512.
Uh,
Uh, so, sir, like I'm trying to train a model, but it is taking very long time, and along with that, sir, it is it is not diverging, but sir, it is not training. Like the server is not taking that.
Training means like you're saying that you're not able to train it, or like your memory is not
Yes, sir. I'm
accepting
not.
it.
Yes, sir.
It's
Yes, sir.
beyond the capacity of the memory. So again, that is very crucial part, and it will come later. So I'll come to the architecture part, CNN architecture part, then I'll explain everything, like what are the things that is required and how we have to calculate it. Like how we are going to calculate the memory requirement, how much memory you need for the particular architecture, how many parameters that you need to learn, how many computation you are going to do. So these all the things will be covered. Just wait for a few more lectures. Maybe next lecture or next to next lecture, maybe we'll be starting this.
Okay, sir. See, my questions still remain unanswered, sir. There.
Please.
Here, 3072. I'm just that's my vector size of a one image. Then I'm just converting that into 100 there. Okay, I'm just trying to reduce. By that, I'll reduce the pixel clarity. I'll reduce the pixel clarity to 100. How will I be able to detect an image by doing that? That's what is the question, sir.
No, so here, actually, in this case,
maybe different logic.
Yeah. When I was discussing this fully connected, maybe in the previous class, then what I said that here we have, like, if you just use the linear classifier, that is like just one W. In that case, what we were doing, we were taking the 3072 values, and finally we are reaching to the 10 values, because the score for every class. So we have 10 classes, then score for one class, like all the classes. That was the goal in the case of linear classifier.
Okay.
So here what I said that one row is like it is like template of one class, because you need you need 10 rows for getting 10 values.
Yeah.
And one template is playing role of we can say it's like classifier, or we can say like template of one class.
Exactly.
Okay.
Correct.
Okay. Now in this case, we are directly not moving to the 10. Instead, first we are going to some other values, and then it's just like we are in a single shot. We are not saying that models should solve this very complex problem. Instead, we are it's just like divide and conquer approach, or going in a hierarchical manner. So first you take 307, because here we have, in this case, we have started with 3072 values, and then directly you move to the 10 values in a single shot. Here what I'm saying that start from 3072 values, then go to the 100 values. So this 100 is, again, you can consider as a class score only, but these 100s are not the actual class. This is like hypothetical classes.
Okay, sir, I got it.
So already I've explained in the previous class all this stuff.
Sir, in here, random, the range you have given, sir. What is the basis on which you have given the random, sir? If I consider MNIST as a data set, so should I be considering the minimum and maximum values of the MNIST data set collection over there? How is it, sir?
Random for what?
Random W1 and W2 random range you have considered there.
Yeah, random, that is like normal distribution. Rand N is like normal distribution. So N is like, it's because this is the matrix. So in this matrix, you have to fill the values. So initially, just we are taking all the values from the normal distribution and putting here, just random values from the normal distribution, because this is the matrix now. So it should be having all the values now. You just define the size of the matrix, but you also need to fill all the values. So at the starting, you don't know what would be the W. So just take the random values.
Okay. If I correlate that, should I correlate the matrix of 10 rows consisting of image data?
Yeah. You can just see as a 10 into 3072. This is the matrix. Suppose you have the linear classifier. So let us assume that we have only one W, and you are going from 307 to 10. Now this is the matrix, but But again, in this matrix, you should be having all the values now. So from
Okay.
where we should pick the values. So initially, just pick the values from the normal distribution.
So as I understand, sir, 3072 is my input, 100 is my initial classification, and that further class, I'm again further classifying that 100 values into 10 values to
Yeah.
convert my input to output.
Yeah.
Correct.
Yes.
Okay. Okay. Thanks a lot. Thank you.
So here also you need one extra matrix. So it is like this will be 10 into 3072, and this will be what will be the size of this matrix.
Exactly, sir. And the number of epochs here, 2000 you have decided there. That's also based on experience. That's also based on
Based on experience, but it's like just we are giving the maximum range. And let's see in between if we get suppose your model is getting saturated, like you reach to the loss close to zero, or maybe suppose your model is not, the loss is not getting changed, and you just observe like for a certain epochs, it's not getting changed, then you can stop.
Okay.
So
Okay.
again, you can consider some stopping criteria, and then you can go with that. Let me just tell you one more thing here. I have considered here 64 images. And in this data set, what I am assuming that we have only 64 images. So that's why we are able to process 64 images at a time in the epoch. But in reality, like suppose you are going to solve your problem, then it could be having maybe millions of images. Then you cannot go with millions of images at a time.
Yes, sir.
So what we do, you first divide into batches, okay? And then this will be like epoch. And in one epoch, you will process all the batches.
Okay.
And for one batch, you'll do the back propagation of everything, update the W, do for the second batch, and so on.
Okay.
And once you are done for all the batches, that will call as a one epoch or one iteration.
Yeah.
But once your model is fixed, everything is now you are happy with the model, then you just use it. Then process very fast, because just it will take the image. Now this is the export. So it will take the image and give you the label.
Okay. Okay, sir. Okay. Sure. Thanks. Yeah. Thank you.
I'm asking, are these PPTs sufficient for practical purposes, not for exam, but other than that?
No, I think whatever I explained here, if you write in this way, this is the code only. So in the similar way, you can design like this type of, because this is like you're writing. Yes, you're just making the neural network. So you can do in a similar manner, but it's like I have done in a NumPy, but instead you can use some even more powerful library like PyTorch or maybe Keras that can even give you more advantage or more flexibility. So what I can give you, like it's my suggestion to all of you that please go through the PyTorch tutorial and just see the basic neural network architecture. You'll get to find all the things what I explained here: forward pass, backward pass, input defining this, but on the real data set. So that will give you even more understanding of this concept.
Sir, for the exam purpose, these PPTs are sufficient, no, sir?
Yeah. For exam purpose, this
Classes are sufficient.
Yeah. This we already have covered almost all things, like everything, whatever is required. So I think this is sufficient for the exam purpose. But for the practical, from the practical aspect, you can just walk through the PyTorch tutorial. That will give you even more understanding, like how we do this thing practically. Okay. It's very, very simple. Let me just tell you, practical part is very, very simple. Even whatever I told you, even if you use the PyTorch, it's even more simpler than this. You can just write in a single line. You don't need to write this thing, back propagation. They will just take care of this. Here, just for the sake of explanation or for the sake of understanding, I have given this thing. Again, we'll also deep dive into this back propagation. But these things are not required while doing the coding. PyTorch is already having all those gradients. They already have the flexibility for calculating the gradients. So you just provide the loss function, whatever loss function you are. Again, they are also having all the loss functions. You just use one from there and just pass the argument like prediction and ground truth, and it will do all the things. So it will calculate the loss and it will give you the loss. You no need to write any. Just you have to define the architecture. That's all. And even defining architecture is very, very easy. No need to go in this way. Just write layer 1, give the input size, provide the input. That's all. So very, very easy. Let me just tell you, you just first you go through that PyTorch tutorial. And if you feel that no, we need one lab class on this, then we can further do it. But first you just go through that, walk through that and see it. Like it's not difficult. It's very, very simple.
Okay, sir.
If you know this concept, then this will be very, very simple.
Sure, sir. Sure. Thank you.
Okay. Then if there is no further question, then I'll stop here. Thank you.
Thank you, sir. Thank you. Thank you.
Thank you.